Welcome to lecture 403N03. We'll try in this lecture to talk about phasors, their meaning, their representation using complex numbers, how to go from the time domain to the phasor domain, and vice versa, and how to use this to analyze circuits when we have sinusoidal excitation. So the main application of phasor analysis in electrical engineering is really the analysis of circuits with sinusoidal excitation. So we'll see how this is gonna go. We'll start now to write the theory or of applications of phasors. There are three main types of analyses we use in electrical engineering. The first one we have seen already is DC analysis. And this where all the sources are not time dependent, they are constants. Like a battery is equal to 50 volts, a current source is equal to 5 amperes. All these sources do not change with time. So once you find the current and sources in the circuit, it is the same, the current and voltage in the circuit, it is the same for all time. It's really, it's called DC analysis, direct current analysis. Direct means it does not change with time. Second type of analysis we can do is a transient analysis. This happens when the sources are changing with time in an arbitrary way. For example, we have a voltage source which is exponential, decaying exponential with time. Or we have a current which is maybe like a step function or something of that sort. So these are general time domain functions of time, and these will result in all types of currents and circuits and all types of currents and voltages in our circuit. The last type of analysis, which is the one relevant to phasors, is really the AC analysis. AC analysis means that you have sinusoidal excitation. So the voltages and currents are all sinusoidals. Usually for linear circuit, this means that you have a source which is sinusoidal, and all the currents and voltages in the circuit as a result will also become sinusoidal with the same frequency. They will differ only in amplitude and phase. So these will be the only two different things. So in that way, all voltages and currents can be represented by phasors. So I'm going to repeat this again. A phasor is nothing but a representation of a sinusoidal signal. If you have a linear circuit and your source is sinusoidal, then the currents and voltages everywhere in your circuit will be also sinusoidal with the same frequency. They will only vary in terms of amplitude and phase. So the amplitude and phase information, we combine them together to create what we call a phasor. So the phasor contains the amplitude and phase information about different electrical quantities, including currents and voltages. An alternating current signal, the term alternating current is usually used to refer to sinusoidal signals. So this is an alternating current signal. It simply oscillates between the maximum and the minimum over a certain period of time. The time it takes for the cycle to repeat itself is called the periodic time. The general expression for a sinusoidal signal or for an AC signal is V equal to V max cosine omega t plus phi V. So here you can see there are the parameters of this expression. Vmax is the maximum value. So when the cosine is 1 at certain angle, then the voltage value will be equal to Vmax. So Vmax here is really the big value here. Phi V is the phase. So this waveform can be shifted to the left or can be shifted to the right. Right now, for example, in this figure here, you can see this is minus cosine, because at time t equal to 0 you have minus the maximum. So here the phase shift for this one here, it is shifted by 180 degrees. So this phi V is 180 degrees. It's a half cycle shift. Omega is the angular frequency. You can see it's cosine omega t. Omega t, this term determines how fast the signal changes with time. The higher omega, the angular frequency, the higher the change in time. And omega has units of radian per second, and it's equal to 2 by f, and f is our frequency. F in frequency in hertz. So omega is, we call it the angular frequency, radian per second. And if you remember, when you multiply radian per second multiplied by time, which is second, you get radian, because the angle in this case has to be in radian. F is the frequency in hertz. Omega is equal to 2 by f. F, anyone who studied oscillations know that the frequency is 1 over t. So 1 over the periodic time will give you the frequency. The periodic time determines how fast the signal is changing with time, and the frequency is the inverse of the periodic time. So and the periodic time, of course, is in seconds. So these are all the terms that we need to know for an AC signal. Now, the average of an AC signal is 0. Why? Because if you take over a complete cycle from here until it starts to repeat itself again, you will see that we have positive part, we have negative half cycle, and we have positive quadrant. So positive quadrant, positive quadrant, and then negative half cycle. So the total area, these two positive areas will cancel this negative area. So the average of an AC signal, or the mean of an AC signal, is essentially 0. So in order to be able to use it in electrical engineering, usually we rectify it. We have to use rectification. So usually we have a rectifier, as we'll see later. There's rectifier, rectify the negative part, and then the signal becomes something like this. It becomes a rectified signal, and this signal we can smooth it out using all type of circuits and so on. And then this is what we use really to create the DC voltage used to operate all types of devices. Now let's consider an example, very simple example, just to familiarize yourself with the notations. Well, I'm asking here for you to determine the amplitude, I'm asking to determine the frequency and the periodic time, or the period, of the signal V of t equal to 200 sine 377t. Remember, the standard form for a sinusoidal signal is a cosine, but a sine is nothing but a cosine that was shifted by pi over 2. So we can put this one again into the standard form of a sinusoidal signal. Of course, this is here is the frequency, is the amplitude, it's 200. This one here is omega. I said, remember, sine omega t or cosine omega t. This is omega, and whatever is added to the angle inside is called the phase shift. So we write this signal in the standard form. 200 sine 377t is equal to 200 cosine 377t minus pi over 2. A sine is a cosine that was shifted to the right in the positive t direction by pi over 2. This has to be very clear in your minds, because you're going to be using this over and over again. This is a cosine signal. If I shift it this way, by just pi over 2, so that I bring this point here. If I do that, this becomes a sine. This is why any sine is a cosine minus a phase shift to pi over 2. And notice that when I move the signal, I shift it in the positive t direction, I subtract from the phase. I don't add to the phase. And many people get confused about that. But this is how the formulation for sinusoidal signals go. So for this one, we have all the information that we need. This the maximum value is 200, omega 377, but this omega is nothing but 2 by f. So I can simply divide two sides by pi. And remember, pi here is 3.14. If you divide that, because this whole thing is a radian per second, so you divide 377 by almost 6 point something, you get 60 hertz. If you want to get the periodic time, or the period of this sinusoidal signal, it is the inverse of the frequency. So it's 1 over 60. If you divide 1 over 60, means it takes 16.67 milliseconds to complete one complete cycle in the time domain. Of course, here phi, the phase shift that we have inside the cosine, is equal minus pi over 2. And we'll be using this phase shift very often. So this is a sinusoidal signal, and apart from the frequency, if I ignore the frequency, this signal is really characterized by two things, by the 200 and the minus pi over 2. Because if I take this information about the frequency as implicit, as known already, then all I care about to characterize this voltage or this current is the amplitude and the phase. One important property of AC signals is the concept of the root mean square, RMS. And in electrical engineering, usually when a phasor is given, without determining the nature of the amplitude given, we call it usually RMS. What does RMS mean? If you have a sinusoidal signal, this is a sinusoidal signal, okay? What we'll be doing, we will do as this name implies, root mean square. First, we'll square this signal. So when you square it, you get this squared signal, okay? And then we'll take the average of this squared signal. So try to take the average. And then we take the square root of the average. So you can see we do 3 steps. First, we convert it from a sinusoidal signal with 2 polarities to a squared signal with only 1 polarity. So this one here. And then we take the average of this signal, so this will give us a number. And then we take the square root of this number to be able to get the RMS value. So let's see how we can get this one here. If I have a current, and this current is given by I max cosine omega t plus phi I. This is the amplitude, I max, omega is the angular frequency, phi I is the phase. If I square it first, I get this time domain signal. So this is a cosine square signal. It does not have any negative values, always positive. Now, I expand the cosine squared as 1 plus cosine double the angle. This is one trigonometric identity. So the cosine squared of an angle is 1 plus cosine double the angle. So I did now the first part. I square the signal. And then I take its average. Its average mean you integrate over the complete period. So from 0 up to t. This is a complete period for the cosine signal. And then divide by that period. This is the averaging. This is how we average a signal. So integrate from 0 up to t, and then you divide by t. Now, the average, as I explained to you earlier, the mean value of a sine or a cosine signal over a complete cycle is 0. But this is a cosine with double the frequency, so it has even double number of cycles per one periodic time. So this one as well, its average will be 0. So if I want to draw it for you, if this is my cosine, okay, then the signal, which is cosine double the angle, will look something like this. It's faster. So where this one finished 1 complete cycle, this one finished 2 complete cycles. Okay, something like that. It goes double. It's way faster signal, but still it has a positive area and negative area equal to one another. This is why the average of this term, or the integral from 0 to t of this term, will be 0. I'll be left only by this one. When I integrate 1 dt, I get t, put the upper limit, which is the periodic time, and then divide by periodic time, they cancel out. So you end up that the average of the square of the signal, of the sinusoidal signal, is I max squared over 2. I max squared over 2. Now, if I take the square root of that, I get I max over square root 2. And this is a relationship you have to remember. The RMS value of a sinusoidal signal is equal to the maximum value divided by square root of 2. And 1 over square root 2 is simply 0.707. So for voltages, the RMS value of an AC signal is simply the maximum multiplied by 0.707. The RMS value of a current is simply equal to the maximum value of the current multiplied by 0.707. And you will see later the meaning of this one. It really gives you the value of the DC voltage or current that will create exactly the same average power. This is the meaning of this root mean square value. But just remember, it's nothing but the maximum divided by square root 2 after you follow this derivation. You don't have to remember this derivation, just remember this last result. Now let's take a look at another example. Determine the instantaneous and the average power dissipated in a resistor R connected across a voltage source V of t equal to V max cosine omega t. So we have here a resistor, and it has across it a voltage source, but this voltage source is not really constant. It's varying with time as a sinusoidal signal, as a cosine signal. It has an amplitude which is equal to V max. It has a frequency which is omega radian per second. would like to determine the power, the average power dissipated in the resistor. We know from our studies so far that if you square the voltage and then you divide by the resistor, for DC signals it gives you the power. But when the voltage is changing with time, when it is not really a constant, when it is V of t, when it's changing with time, this really gives you what we call the instantaneous power. What is the power delivered to the resistor at that instant of time? And of course, this varies with time. In order to determine its average, we have to integrate the average over a complete cycle. So now, if you have this power, the power by definition, if this is a sinusoidal signal, if it's going to be Vmax squared multiplied by sine squared omega t. I here use the sine, not a cosine. It does not really make a big difference, just a phase shift of pi over 2. It's simply a sinusoidal signal. A sine squared can be replaced by 1/2 1 minus cosine double the angle. Okay, so this is still the instantaneous power. So you can see the power is varying with time. When cosine 2 omega t is equal to 1, this term will give you 0. So at one instance of time, there is no power delivered. At some instance of time, when this says equal to -1, the power is maximum. So the power delivered to the load is really varying with time. In order to determine the average power, we integrate over the periodic time from 0 up to t, and then we divide by the periodic time. And as I explained earlier, the integral from 0 to t of cosine omega t dt will be 0. And the integral from 0 to t of cosine 2 omega t dt will be 0. And the integral from 0 to t of cosine of any multiple of omega t, as long as an integer multiple, 1, 2, 3, 4, 5, dt will be equal to 0, because this will give you even a sinusoidal signal with higher frequency, but still the positive areas cancel the negative areas. So the only term that's going to remain here is Vm squared over 2r. If you integrate this term, you multiply it by t and then you divide by t. Then now we know that the average power for a sinusoidal source is Vmax squared divided by 2r. But Vmax over square root 2 is the RMS value. It's what we call the RMS value for any sinusoidal signal. So this means that the average power dissipated in the resistor in this case is the Vrms squared divided by R. What does this remind you of? This is the same expression we use for the power in DC examples. So now we were able to show that the power delivered by a sinusoidal signal is equivalent, or the average power delivered by a sinusoidal signal is equal to a power delivered by a DC source with value equal to Vrms. So Vrms is really an equivalent DC voltage that gives exactly the same average power. Okay, so this is why the term Vrms is good, because it simply takes us back from an AC to a DC signal. It supplies exactly the same average power as if this is a DC problem. So now we move to talk about the phasor. What's a phasor? A phasor really contains the information about the amplitude and the phase of the signal. For example, here I'm showing you 3 signals. This is a cosine, it's not shifted. Okay, it has certain amplitude and its phase is 0. So this one here, the black one, has a phase of 0. Okay, the red one, you can see the red one, there is one is a cosine that was shifted to the right. It was shifted in the positive t direction. So this one has a phase shift less than 0. And I explained to you, when you move a signal, a cosine, and when you shift it in the positive t direction, you are actually subtracting certain phase from the cosine, from the angle of the cosine. You can see another cosine there, this blue cosine, this was shifted to the right. So it has a separate amplitude, different amplitude, but its phase shift is positive. So each one of them can be given by its phasor, and the phasor is nothing but we can really use it as usually when we write it as Vrms e to the j phi e to the j phi. So this is really what we call the phasor of the quantity. It is simply the RMS value multiplied by e to the j phi. And remember, this RMS value is nothing but the maximum divided by square root of 2. If you want to take the signal back in the time domain, what you can do, you can multiply the phasor by e to the j omega t. Of course, here, if you do not take into account the square root of 2, you have to multiply by square root of 2. But I would like maybe to focus on this one. What does this mean? If I take this term that we have here, this term here, if I multiply by e to the j omega t, I get this term. So this is the phasor, so V multiplied by e to the j omega t will give you VRMS multiplied by e to the j, and then I open a bracket omega t plus phi. If I take the real part of this one, this is e to the j theta. E to the j theta is equal to cosine theta plus j sine theta. So the real part of this term will give you the cosine. So if you take the real part, this will give you the VRMS multiplied by the cosine of omega t plus phi. So, and this is how we go from the phasor quantity to the time domain quantity. Remember, here I did not multiply by square root of 2, but of course, in order to get the actual value for the time domain quantity, you have to multiply by square root of 2. If this was an RMS, and in every signal that I'm going to be giving you, I will tell you whether in the time domain, whether this is an RMS or it's a maximum. But usually when we give a phasor, it is usually an RMS value. A phasor also is represented in the frequency domain by a line that has a certain magnitude or certain length and certain directions. For example, here, this is the length of a cosine signal, and this is its angle. This is the length. By length I mean really the amplitude here. This is the amplitude of another cosine signal, and this is the angle. The angle here is positive; it's certain phi. This is a negative, another phi. So, so this is really a way of representing the phasor. The possibility of doing it is to do it using the maximum value, but usually, as I said, it is usually represented by the RMS, unless otherwise stated. But here I'm saying the maximum is the amplitude e to the j phi. Remember, it is not really a function of time, because the frequency domain information or the frequency information is not attached. In order to go back to the time domain, you have to multiply this by e to the j omega t, and then you take the real part. This is how we go back from the phasor domain to the time domain quantity. I don't really put big weight on this representation, but just remember this is called the phasor representation. A phasor is represented by a line. It has a length equal to the amplitude, and its angle is equal to the phase shift. And this phasor really rotates with time. But when they draw it, usually don't worry about this rotation with time. Okay, let's take a look at an example just to clarify the result here. We have a time domain sinusoidal signal, and it's given by 5 sine 200t plus pi over 4. We would like to write the corresponding phasor. So for the corresponding phasor, we have to determine what is the amplitude and what is the phase. And remember, in this course, when we talk about amplitude and phase, we talk about a cosine, not a sine. So you have to put this back again in the form of a standard cosine. Okay, so now let's see how we're going to get the phasor of this time domain quantity. So the quantity that we have is 5 sine 200t plus pi over 4. And if I make it as a cosine, I have to subtract from the angle pi over 2. So this becomes minus pi over 4. So this cosine is nothing but the real part of the amplitude e to the j, the rest of this quantity. Remember, this is something you have to remember all the time, that I have to write it for you here, that e to the j theta is equal to cosine theta plus j sine theta. So if I take the real part of e to the j theta, it becomes cosine theta. So this cosine here is nothing but the real part of the corresponding complex exponent, e to the j 200t multiply, of course you can write as one exponent, e to the j 200t minus pi over 4. But when you have two exponential terms like this one, you can separate it into the product of two terms. This is the t term, which we do not include, and this one contains a phasor term. This is 5 e to the g minus pi over 4. Here I left it that way in terms of the maximum, but in most cases, we can simply, if you want to write it as a phasor in terms of the RMS, this is how it should be. It should be 5 over square root 2 e to the minus j pi over 4. This is in terms of the RMS. So I write it here as V RMS, okay? But if I want to take it back to the time domain, I have to multiply by square root 2 in order to convert it from an RMS value to a maximum value, which is equal to 5. Okay, so it's just a notation. We have to select it and stick to it. So for this course, I will assume that all the phasors are in RMS.